Welcome to this course on satellite communication systems. In last lecture we have learned a couple of things in the introduction. One of them is the satellite is a form of wireless communication, but it covers a large geographical area. That is one of the basic feature of satellite communication. In general, also we have seen that satellite communication or communication satellites are microwave repeater. Other frequencies are also available, but generally it is microwave repeaters. Some of the brief features of international and Indian satellites also we have seen, like Intelsat, Inmarsat, IP Star, Iridium, INSAT, etc. Then we have learned about certain technical terms which are used in this service. Some of the terms are transponder, we will come to know later what is it. Then terms like BSS, FSS, MSS, etc., like broadcast satellite service, fixed satellite service, mobile satellite service, high rel, that is high reliability, LNA, low noise amplifier. Some of them you are familiar, for some of them it is new terms. We will frequently use these type of terms. Also we have seen the frequency bands allocated for these services, like fixed satellite or broadcast satellite services by International Telecommunication Union. That is a international arrangement for sharing this natural resource, which is a large wireless frequency band for different types service. Satellite service is one of them. And also we have seen just a few technical units that is used, like dBW, gigahertz, etc. We will frequently use these terms also. We should know the meaning of these. Most of you know about it. Okay, with this very brief basic knowledge, we will start on the satellite communication system. Yesterday we have seen that it consists of three segments: space segment, ground segment, and the propagation medium. Very briefly this can be described in three segments. Now for space segment, it consists of the satellite which is in the orbit and the ground station which controls that satellite. Now let us know something about this orbit. Orbital mechanics or orbital dynamics is a very large subject, and we are looking at it from the communication angle. So we will try to see those features of the orbit of this particular satellite orbit that will affect our communication system, like change in frequency, like the communication delay, like the noise, like the power. These are certain things which will be affecting our communication system, which are the effect of orbit. So we will start with orbit, and in this course I would try to go with some examples in between. So all of you must have a calculator ready with you in hand, so that in between whatever I try to show, some formulas or numbers, you try to calculate and verify, and you will get convinced that yes, this is correct. Okay, that is how we will learn. Now the basic knowledge about the orbit, in that what we are going to cover in general, one is at the orbit, what is the velocity of the satellite, what will be the orbital height and the period and their relations. Also the satellite, whether it is visible from the location where you are a user, what is the visibility of the satellite, and at which direction, which angle you can get that satellite. Then briefly we will learn about how to reach that orbit, how people try to reach the orbit, and then this orbital perturbation, the changes in the orbit and the effect of the orbital location of the satellite on communication system also we will learn. So very briefly, these are the major subtopics that we will cover. Now let us go back to to our school days. That is okay. Before that, let us look at this. This is a picture taken from the internet, and a satellite which is launched from the earth here. It looks like a cube packed, and then it goes into a particular orbit which is called transfer orbit, and from there some rockets are fired within the satellite and it takes a different orbit, and this orbital height is slowly changed, and during that process the solar panel etc. are getting deployed, and then finally it reaches the intended orbit. This is a pictorial representation from one of the internet sites. Now, at each of these positions, satellite attains certain velocity, certain height, and it takes some time to orbit that. Let us recollect from our school days the laws of planetary motion, which was initially stated by John Kepler, and all of you are familiar with that. So, we need not go into detail, just to recollect the things. This is a natural law. What John Kepler stated is the planets orbit in elliptical path with the sun at one of the focus. Here is a sketch of that. It is a natural force. So, this can be utilized between two bodies having mass, and therefore, it can be used that a satellite can move around the earth. Instead of sun, let us call it earth now, and a satellite can move around the earth, and a natural law is it can move in a elliptical orbit. A special case could be a circular orbit. So, this is natural law, and that natural law gets affected by the velocity and the time period and the orbital height etc. We will try to calculate those numbers. There is a second law which states that the line joining the planet to the sun, sweeps out equal space in equal time. That means, this area to travel the planet over this much arc will create this much area which is swept. The time taken to travel for this arc will be same as time taken to travel this arc which has the similar area. This has a very good implication, that is, you can see always that here the time taken and here the time taken are same. Therefore, relatively the time taken here is slower compared to the time taken here is faster between them. And if it is a ellipse, there is a perigee and apogee, the way we define. So, at perigee the velocity will be larger, faster compared to at apogee. So, this is a very important law. We will try to utilize this. So, velocity of the satellite is slower at apogee and faster at perigee. This is the second law. And the third law of planetary motion states that square of the period of a planet to orbit is proportional to the cube of mean distance from the sun. So, these things can be derived. Let us say for a circular orbit, you have learned this thing in school days, that centripetal force is equal to centrifugal force, then it will move in a circular orbit. And if we take m as mass, v as velocity, r as radius of circle, and a is acceleration, the outward force is equal to mv square by r, and that inward force is m mu by r square, or mu is a constant whose value is 3.98 into 10 to the power 5 kilometer cube per second square. Remember that this is in kilometer. So, if we have to calculate sometime in meter, we have to look at this number and change some of the numbers here. So, this mu will come very frequently in our calculation. So, when f in and f out are equal in a circular orbit, we get velocity square is equal to mu by r, or velocity is mu by r root over, it is in kilometer per second. And from this we can find out the time period to the orbit, that is time is 2 pi r, that is the circumference, by velocity, and replacing the velocity t square is equal to 4 pi square r square by v square, by squaring this term and put the value of v square, that is mu by r. So, it becomes 4 pi square r cube by mu, or t square is proportional to r cube. That is what is stated by Kepler. Now, we know the circle is a special form of ellipse. So, therefore, let us look at ellipse. Ellipse, if you remember, that is from the focus to the perigee we can call rp, focus to the apogee the distance is ra, and there is a semi major axis and eccentricity which are expressed in terms of ra and rp are like this. These are school days expressions. So, if we put the planet or satellite in the elliptical orbit, at r a the velocity will be v a square is equal to mu by 2 by r a minus 1 by a is the semi major axis, and velocity of at perigee is r p will be coming. So, therefore, you can see depending on the r a and r p, the velocity at apogee and perigee is different, and t square is represented by 4 pi square a cube by mu, just like in circle it is 4 pi square r cube by mu. These are the formulas which you know. Now, let us use this formula. This is where your calculator will come into picture. Let us use the formula and try to understand the implications. Let us try to make a table where orbital height we increase in numbers like 1000 kilometer, 20,000 kilometer, 40,000 kilometer, like that, and correspondingly for each of these orbital height we calculate the velocity and orbital period. Try to remember, try to see that I am using a term orbit height. Orbit height I am calling the height normally where we stand from there, how high it is. So, therefore, I am assuming that this is orbit height is from surface of the earth, but the calculations were based on the center point of the circle. So, therefore, the radius of the earth has to be added to this to get the from the center what is the radius of the orbit. So, to find out the radius of the orbit for 1000 kilometer orbital height, it will be 1000 kilometer plus 6378. This is just a assumption because earth is not exactly sphere. We assume here that earth is a sphere with this type of number as a radius of the sphere. So, this radius of the earth plus this orbit height to be added, and then you do the calculation of velocity and orbital period. You try? You must try, just do not look at the number what I am going to show you, those numbers have to be verified by you. Anyway, I will show you the numbers. Let us say for 1000 kilometer orbital height you get the velocity 7.35. This decimal number, do not get much worried if it is some slightly different number appears, this is calculated error, let us say, but it is more than 7 kilometer per second at 1000 kilometer orbital height. That is from the center of the earth it is 6378 plus 1000, 7000 kilometer from the center of the earth, if we assume earth as a sphere, and corresponding orbit period is 100 minutes, slightly more than 100 minutes, which is in second 6307. That is what this calculation shows. You get the similar number. So, it is quite fast at 1000 kilometer orbit, 7 kilometer per second, and it revolves around the earth in 100 minutes. That means, for a short time it will be visible to you on the earth, because you are standing on a earth surface, and just goes out of view, it will appear after about 100 minutes to you. Let us see what happens at 20,000 kilometer. At 20,000 kilometer, the velocity, again you have to calculate 20,000 kilometer is orbital height, and you have to add that surface the radius of the earth as 6378 in this case, and you will get a velocity number slightly more than almost 4 kilometer per second, slightly less than 4 kilometer per second, and orbital period is 42,600 second. Velocity has reduced. Now you try for 40,000 kilometer, and then you get a number like this, almost 3 kilometer per second orbital period, and orbital orbital velocity 3 kilometer per second, orbital period is 99,300 or 400 seconds. So looking at the table, these numbers gives us some indication, that is, as we increase the orbital height based on natural law, we see that at those orbital height, when you increase, the velocity of the satellite or that particular spacecraft is reducing, and it is taking more time to complete the orbit. It is a circular orbit. So one of the observation from this table is satellites with lower orbit height goes out of visibility in a short time. Now you are a communication engineer. Look at it from the communication point of view. If you want uninterrupted communication, then only for few minutes you will be able to use that satellite as a repeater, and quite a long time you have to wait, almost for 1,000 kilometer, more than an hour, more than an hour or hour and a half, you have to wait for that repeater to appear again. So you start communicating, wait for 1.5 hours, again you start communicating. It is irritating. For real time communication, it is irritating. There are some form of communication where you store and forward, you can use it, but then it is one of the important observation. So for uninterrupted communication, satellite should be always visible. So how we can do it? There are possibilities. One simple possibility is shown here, that okay, let us put a constellation of satellites, a large number of satellites at low Earth orbit, so that one satellite, if you are here, one satellite goes out of visibility, the second satellite will come. If that goes out of visibility, the third satellite is coming. But then there is that handover, takeover mechanism, and lot of other complications are there, but still some repeaters in the sky is available for you to support your communication. This is one way. There is another way. The other way is make this satellite relatively stable with respect to the movement of the Earth. Now how that can be done? That can be done only if the satellite period is made same as that of revolution of the Earth on its own axis, because Earth is moving. Now if the Earth is moving, that revolution, whatever time it takes to revolve once, if the orbital period is same as that, then it is relatively stable. So this is one important observation we have seen. And how much a Earth rotates in its own axis, complete one axis, we have seen that it is called Earth revolves around its axis in a day, right? Now what is a day? What is a day? We know the sun is there, Earth is there, and if we join center point of the sun and center point of the Earth, a point P crosses the surface of the Earth. So for the point P, observer sitting or standing at the point P, a day is a time for consecutive occurrence of Earth sun center and the P in one line. That means at this instant P is here and Earth is moving like this around sun. So at some other instant P, next consecutive instant, when center of the Earth, P and sun all comes in a line, we call it a day. At 12 o'clock in the noon you stand, you have a, let us assume that sun is out overhead to you, and next day at 12 o'clock in the noon, sun will come again overhead. This difference of the time is called a solar day. Let us rotate the Earth. Earth is rotated, so P is also rotated accordingly. So if you move 360 degree from here, P is here. It is not in the straight line of center of the Earth. P is not reaching the center of the sun. Then we move Earth a little more, and after some more revolution of the earth we get center of the earth P and sun at the same line. So, from here to here that is a solar day, but earth has revolved more than 360 degree for a solar day. So, that we can define this is also a day which we will call sidereal day, another term, that is one revolution of earth in its axis. So, one revolution of earth in its axis is less than a solar day, because solar day took more time that to reach the P, center of the earth and center of the sun in same line. It can be calculated that it is 0.987 of a solar day, which is 23 hours 56 minutes 4 seconds roughly, which in terms of second comes out to be 86,164, whereas a full solar day 24 hours is 86,400 seconds. Now, in this process what we have learned that if we use this time period, which is one revolution of the earth 360 degree is this time, and use this time period, we can get the orbital height. So, what is the orbital height of a circular orbit satellite with a period of one sidereal day, that is one revolution of earth? Let us recollect that formula of the time period of an orbit, that is T square is equal to 4 pi square by mu and r cube, and from that the r can be calculated r as T square mu by 4 pi square, 1/3 root of that. Let us put the number sidereal day. T is 86,164, T square 86,164 square. Mu, if you recollect, it was 3.986 into 10 to the power 5 kilometer cube per second square, and of course 4 pi square, and 1/3 root of that. So, that you get a number roughly about 42,164 kilometer from the center of the earth, assuming earth as a sphere. So, from the center of the earth, if it is 42,164 kilometer at that orbital height, if it rotates in the same direction of the earth, then the satellite will be relatively stable to a observer on the earth. So, assuming spherical earth with radius of 6378, the orbital height again from the surface of the earth is 35,786 kilometer. These are all rough numbers, roughly sometimes people call 36,000 kilometer. If you recollect, yesterday or the last lecture we have said that at 36,000 kilometer height it will be relatively stable. So, this is the calculation which says that orbital height of this 36,000 or 35,786 kilometer, assuming this is the radius of the earth, it will be relatively stable. Now, there is certain definition. At this height the satellite is moving in synchronism with earth rotation. When it moves in the same direction as the earth revolves, that is west to east, it is called geosynchronous. It is synchronism, so it is called geosynchronous orbit, or in short GSO, geosynchronous orbit. Okay? But still there are some more information you need. Let us see that. When this orbital plane is same as equatorial plane, then for an observer on earth's surface the satellite seems to be at a stationary point above the equator. You just see, just imagine earth as a sphere and the equator is extended, cut the earth in between. So, equator is extended as a plane, and on that a satellite is orbiting on the equatorial plane. So, orbital plane is same as that of equatorial plane. Just here I am trying to show you a view that is as if this is the north side of the pole and this is the earth, and this is the equatorial plane at the center of the earth I cut, and satellite is put here which is orbiting on this plane. That means satellite orbital plane is about orbital plane has no inclination with the equatorial plane. It is just 0° inclination. We can view it from the top of the pole, that is, this is the North Pole from the top, Earth viewed from the pole, and then you can see that equator, Earth bulge is the equator, let us say, and this is the equatorial plane, and on that the satellite is orbiting, and it is in circular orbit. So, eccentricity is 0, and it is moving as Earth rotates west to east. This is west to east, and orbital period is one sidereal day. So, then it is called geostationary orbit, GEO. Other one was geosynchronous orbit. So, this is geostationary orbit. I have put lot of conditions. There is no inclination, eccentricity is 0, in the same direction, and one sidereal day. So, geostationary orbit satellite will have satellite move in the same direction as Earth revolve. Orbital period is one sidereal day, it should be in circular orbit, and orbital plane have 0 angle with equatorial plane. All Indian national satellites which are INSAT are placed in GEO. In short, INSAT satellites are called geostationary satellite. Okay. So, we stop here for this period, and we will continue this discussion on orbit in the next period. Thank you very much.